Hey y'all, welcome back to another round of engineering. And yeah, let's keep going. So last time we covered the idea of superposition in order to analyze a circuit. Now we're going to do something else also involving independent current and voltage supplies. So this is actually skipping back a little bit to chapter 2, and the reason I present it in this order is because I feel like this topic of source transformation, so source transformation, goes better preceding our discussion of Thevenin and Norton circuits. So that's really why I've decided to cover the source transformation at this point in time. Now, to give you a sense of both why the book presents it in chapter 2 and why we're talking about it now, the first thing that I want you to recall is how we deal with circuit simplification with resistors in series and resistors in parallel. And you've got the idea. If we're dealing with equivalent circuits where the resistors are in series, we simply take the summation of each of those resistors in order to simplify the circuit if need be. For parallel, it's not the sum of the resistors, but rather the sum in inverse, and that equals 1 over Req. So we've dealt with those situations and simplifying the circuit in that manner. Okay? And as we'll see, again, as a reminder, we have similar ideas for capacitors, for inductors, and frankly, if you really wanted to, you could say even springs. Okay, so if we go into mechanics, you can think of springs, for example. What we haven't talked about yet is how to deal with sources. Is there a way to do a simplification procedure much like what we did for resistors, but involving sources, V's and I's, rather than R's? The short answer is yes. The long answer is, well, yes, sort of. So, okay, well, let's go at it. And to give you an idea, you already know two of the ways of doing this. So I will highlight those for you so that for completeness, if we have potential sources in series, what do you think we would do? Okay. Call it V1 and V2. Yeah, you probably already got it. You know that the potential, if you will, the equivalent potential would simply be the summation of the individuals. Do it like that. Okay. And where does this come from? This is really an application of KVL, right? As I go over a jump and then over a second jump, that could be modeled as a single jump with a summation of the two potentials. Okay, so hopefully that's not a surprise. How about this one? What happens if I have current sources in parallel? How do I deal with that situation? And hopefully you see again that if I want an equivalent source, if you will, I would again just simply take the summation of the individual current sources. So you could think of a current source pumping into a node of some sort, a second current source pumping into a node, and you could model that as a single one with I1 plus I2. And really, what are we doing there? We're applying KCL. We're thinking about the current flowing in from this direction. Of course, I guess there needs to be an outflow wire of some sort. But the current flowing in from both of the sources meets at the node, and we would take the summation. Now, the glaring omission, of course, would be what do we do when we have potential sources in parallel or when we have current sources in series? What do we do with these two situations? And that's really where this idea of source transformation comes into play. Source transformation allows us to take potential sources in parallel and combine them. Or it allows us to take current sources in series and combine them. It's kind of the way I think of it. Okay. And we'll come back to these two rules. Essentially, what we're going to do is we're going to make a potential source in parallel look like a current source. Okay. Or we're going to take current sources that are in series and make them look like potentials in series. And once we do that, we know how to combine potentials in series, or we know how to combine current sources in parallel. So that's kind of the 30,000 foot overview. Let's get an idea on how we're going to do this. Okay. In fact, we'll just derive the relationship. So here's what the scenario is. Let us consider for a moment a single potential supply and a resistor. So I'll call this R1. And then we will have our load resistor. Okay, so there's my output terminals. And in addition to this this circuit, I have my load resistor. Okay, RL. And now what I want to emphasize here for a moment is that if we are analyzing the circuit to find out properties of RL, and what I mean by that is how the load resistor is going to respond to the input. I don't really care how that input is produced, if you will. From the point of view of the load resistor, it needs to know two pieces of information. It needs to know the potential drop across the load and the amount of current flowing through the load. Okay? So what I mean to say is that I can make this circuit look like something else, possibly. So from the point of view of the load resistor, this right circuit would be indistinguishable from this left circuit. So now I've exchanged my voltage supply with a current supply. I'll call this R2 for a moment. And again, I'll have my terminals with the load resistance, RL. Okay. So what you see here, let's go for a different color, is essentially what do I want to do? I would like to exchange this part of the circuit and that part of the circuit. So what we'll find is under what condition are these circuits the same? Same. And I'll say with respect to RL. So stuff inside those dashed purple boxes, that will change. For example, the power through resistors will change. But from the point of view of the load resistor, everything stays the same. Okay. And in particular, we need to figure out what's the relationship between R1 and R2. What condition has to be applied to R1 and R2 in order to exchange a potential supply in series with R1 with a current supply in parallel with R2. So let us get, first of all, a sense of what is the current flowing through the voltage divider. Well, we have the potential, we have our resistors in series, So the resistors in series simply add, and I have something like this. That's the current in the circuit containing the voltage supply. Now let's go ahead and find out, based on this, what is the potential drop across the load resistor. Knowing the current through the load resistor, we know that the potential drop, put potential drop RL, is equal to the current times the resistance. So I get, and again, we've had this derivation somewhere else, probably in the KVL, KCL lectures. And we get this relationship. So good. We have the current being applied to the load, IV, and we also have the potential drop across the load. Let's now analyze this right circuit. And again, we want the same two ideas. Well, here we realize that we have a current divider, and so we know that the current flowing through R2, or excuse me, RL, so the current going through RL is equal to the initial current, I'll call it I, and then we have R2 over R2 plus L. Well, if this is the current flowing through RL, then we better find the potential drop across RL. Call it VIRL. And again, we take the same idea. We take our current flowing through the circuit and multiply by the resistance. So we have I times R2 RL over R2 plus RL. So let's see if we can use, for example, this top relationship in order to figure out what we need, the restrictions on R1 and R2. Okay. So next, taking the liberty of pausing and writing this down. And this is really what we want to figure out. We want the current in the situation that has the potential supply to equal the output current when we were using the current supply. So I've substituted in the two values that we found, and let's go ahead now and rearrange this equation so that RL is separated from the other stuff. Okay? I'm not solving for RL, I'm just getting all of the terms involving RL to one side of the equation. So let's go ahead and look. Well, R2 plus RL equals IR2 times R1 plus RL. And now I said I want to get RL by itself, so I will go ahead and subtract from this side. So I end up with something that says the potential source minus IR2. That whole rigmarole is multiplied by RL. That must be equal to R2 parenthesis IR1. So I've got a common factor of R2 coming in, minus V. So here's where we have to be careful and really put our thinking hats on. Okay. The question I have for you is the load resistance, the thing that I stick into this circuit. Is that in any way tied to the potential supply or the current supply or these variables that I have used, the resistors that I have used to write up these two circuits? No, I should be able to plug in any load resistor I want. I have this circuit, I plug in a load resistor. Okay. What I want to say is that whatever this value is completely independent of all of these other parameters that I've chosen. So what does that mean? That means that this left side of the equation must be 0. If RL is truly independent of these other parameters that I've used for my circuit, the only way for this equation to be valid is that V minus IR2 must be equal to 0. So pause the video for a moment, mull that over, see if that makes sense. Convince yourself that that's okay. And that's something that will come up quite frequently. We will see that, not in this class, but you'll see that later as you progress further in your career, is that we'll have situations where we have two variables completely independent of each other. This allows us to set sides of an equation equal to 0. It's particularly helpful with a method called separation of variables. That's when it's really helpful. Or another thing that it's called is equating powers. Powers of X. You might see this kind of trick played there as well. So what does this tell us? This tells us that V must be equal to IR2. In other words, if I want to replace my potential supply with a current supply, the current supply value must be the potential supply divided by R2. Okay. But wait, there's more, right? If the left side of the equation is 0, that must mean that the right side of the equation has to also be 0. In other words, IR1 minus V must also be equal to 0. So I get another relationship between the current supply and the voltage supply. I get that the current supply must equal the voltage supply divided by R1. Both of these conditions must be met in order for me to exchange a potential supply for a current supply, like we started off with. What does that tell me? Looking at these two equations, what's the relationship between R1 and R2? They have to be the same. Good. In order for me to exchange, to transform a source, a potential source, in series with a resistor, in order for me to transform that into a current supply, number one, the current supply is in parallel with the resistor, which I will now call R. It is in parallel with the resistor R. And furthermore, if I call this V, then the current supply must be V over R. Pretty cool, huh? Yeah? Good. And conversely as well, if you're given a current supply in parallel with R, if you're given a current supply I in parallel with R, you can change that into a potential supply in series with R. And the value of the potential supply is IR. It's cool. This will actually sometimes help analyze a circuit. Now, the last thing I will mention, and then we'll have to look at more complicated situations. We'll start out easy and work our way up. The other thing that I need to mention, though, is again, recall that you are interested in RL, how this circuit affects a load resistor or a load in general. In other words, when you do a source transformation, you cannot be looking, for example, the current flowing through R. And when I say R, I mean this R resistor here. Okay. You notice in these source transformations that you will change the current going through R. You will change the potential drop across that resistor R. Okay. So if you are asked about finding the current through that resistor, you cannot do these source transformations. Now, if you're interested in something else, some other part of the circuit that doesn't involve the potential supply, the current supply, or this resistor R, then you're free to combine those to make your life easier with the analysis part. Okay? So just be aware, when you do these source transformations, from the point of view of the load resistor, nothing has changed. From the point of view of the resistor inside that source transformation, things change. Okay? So just be aware of that. Okay? Well, let's get some practical ideas on this. How can we use this to help simplify stuff? Okay? So the first part is, what's the source transformation? We now have that. Now let's see if we can take advantage of it. Okay? So let's go ahead and use our example circuit and see if we can apply the source transformation ideas in order to find the current through resistor, the 8 ohm resistor. Now I've chosen that because, as we see from the figure, we have two potential supplies that are on parallel branches, and we would like to combine those in a manner that makes the analysis of the circuit easier to perform in order to get this current. Okay? So go ahead, take a minute and see if you can do the source transformations so that it's straightforward to combine the sources. You got it? Good, 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 good. And as I hinted at, it's unclear how can you combine these two potential sources that are in parallel. If they're in series, we could just add them up according to KVL. But here it's not clear, how do we combine them? But if we can turn these into current sources in parallel branches, then we have an idea. So I'm going to go ahead and start off with the top source. And I would like to change this into a current supply. Current supply. And the first thing that I need to do is identify what value I should do for that current supply. Per our source transformations, we notice that we have a 1 ohm resistor. And that derivation that we had said that I need to take the potential and divide by the resistor to find the current supply value. So here I would just have 10 amps. 10 divided by 1 is still 10. The second issue is that rather than the resistor being in series with the supply, it now has to be in parallel. So I will go ahead and draw my 10 amp current supply in parallel with my 1 ohm resistor. There's the first part. Now, of course, let's go ahead to the second branch. I have a 5 volt supply and a 3 ohm amp, 3 ohm resistor, excuse me. So if I want to replace this potential supply with a current supply, that current supply must have a value of 5/3 of an amp. And again, I need to have that in parallel with my 3 ohm resistor. So I'll go ahead and put those two in parallel here. And I have my 3 ohm resistor. Okay. Now I haven't connected those two, but don't forget we haven't done anything to these wires on the edges here. Okay. So I should have a wire that connects the high and low sides of both of those as such. And of course, at the end of the day, I also have my 8 ohm resistor down here at the bottom. So I have now performed my source transformation. I have turned my potential supplies, which were in parallel, into current supplies that are in parallel. And we know how to combine current supplies in parallel. That's just KCL. I have 10 amps going into this junction. Keep in mind this whole rigmarole that I'll highlight here is all a single node, even though I've drawn extra wires and that kind of thing. It's all the same equipotential. So that's just one node. And we have something like 35/30ths. So I could recombine these. Let's make this even smaller now. 10 amps plus 5/3 amps. That would be 35/30. Excuse me, 35/3 amps. Misspoke there. And then in parallel with that, I have my 1 ohm resistor. I have my 3 ohm resistor. And I have my 8 ohm resistor. Right? Cool. Well, now we are at a situation where, I mean, we approach this however we feel like it. Okay. We could do equivalent resistances. We could simply apply node voltage if we want. We could, that kind of thing. So it's just a matter of personal preference how to further analyze this. Let's see here. How would I want to do it? I'm going to go ahead. Why don't I see that the 1 ohm resistor is in parallel with the 3 ohm resistor. So let's go ahead and find the equivalent resistance of the 1 and the 3. That's 1/1 plus 1/3, since they're in parallel. And we take the inverse. So this is 3/3 plus 1/3. That gives me 4/3. And because I have to take the inverse of that, I get 3/4 of an ohm. So now I have turned this into the current supply of 35/3 of an amp. I have a single resistor that is 3/4 of an ohm. And I have a second resistor that is 8 ohms. Well, shoot, this is just a current divider, right? I've got 2 resistors and a current supply. And so now we can take advantage of our current divider. I won't go through the derivation. We've done that once. Okay, go back to the KVL, KCL lecture if you don't remember that. But at the end of the day, what the current divider does, we can say the 8 ohm current flowing through that 8 ohm resistor is the the resistance of the other resistor. So I'll put 3/4 here, 3/4, divided by the sum of the 2 resistors. So if I take 3/4 plus the 8, well, shoot, 3/4, 8, 32/4. So 3/4 plus 32/4 gives me 35/4. That's the ratio of the current that flows through resistor 8. And then, of course, I need to multiply by the total current. So I have 35/3. You see it, right? You say, oh, goody, goody, Greg. The 4 cancels the 4. And so I have 3/35 times 35/3. And so at the very end of the day, I end up with 1 amp, which we already knew. We knew that from our previous stuff. So we have 1 amp of current flowing through the 8 ohm resistor. Now, of course, this technique, this technique, we'd have to look at the direction of the current supply in order to understand the direction of the current through 8, going from left to right. Cool, huh? Yeah. Well, let's go ahead. Let's find another one. Lastly, excuse me, yes, you could also, now that you've combined your current supply, so last comment here, once you combine your current supply here, yes, you could do a reverse source transformation. Particularly, it'll be particularly useful right here when you have your current supply and your parallel resistor. You could have done a source transformation back to a potential supply. And then you would have had 2 resistors in series, and then you could have added those. So right here, I decided to just do the current divider, but you could do a source transformation back if you wanted to. Multiple ways to skin this cat. Okay, well, let's do another example problem here. How about this one? And again, what we're interested in, we'll notice, is right here we have our 2 ohm resistor. So this is the load, if you will, this is my load resistor right here, RL. So take a minute, let's see, go ahead and do source transformations, see if you can come up with an answer for the current flowing through resistor 2. You got it? Good, good, good. And sometimes it's going to take a little while, especially with these more complicated circuits. I say more complicated looking circuits. Takes a little while to kind of get a sense for where things are. And also it takes a little bit of practice of understanding when something's in parallel, when something's in series. Okay. So let's go ahead. We've got a couple of different options here. One of the options that I latched onto, or that I saw right away, is this 30 ohm or 30 volt and 3 ohm resistor in series right here. So we can take that and we can turn it into a current supply and a resistor. So I'll just pull that out of the circuit for a moment so that we can work on that. We have our 10 volt supply, 30 volt supply. We have our 3 ohm resistor, and we are going to change that into a 10 amp supply and in parallel with a 3 ohm resistor. Okay. So we can put that right there. That's the first one. And notice again the connection points. You want to make sure that the connection points remain the same. How about, let's see, so that's that one. We've also got this guy right here. And you notice again, we have a 2 amp resistor, 2 amps. And that is in parallel with this 4 amp. Boy, I keep messing up my units today. I'm sorry, guys. My brain's just not firing. 2 amp 2 amp resistor and a 4 ohm. Okay. 2 amp supply and a 4 ohm resistor. There we go. Well, let's go ahead and change that, and we'll give us an 8-volt supply. So we have an 8-volt supply in series with our 4 ohm resistor. There we go. So let's go ahead and redraw our figure with those 2 changes in so far. I'll start with this 2 amp 4 ohm supply. And the key thing is, notice I've got to make sure that it connects to the circuit in the same way. So I'm indicating the top node and the bottom node where those 2 meet, where those 2 are, a separate piece. And so I'll go ahead and replace that with our 8-volt supply. And our 4 ohm resistor. And notice I could put that 4 ohm resistor. It doesn't matter if I put it above or below. Okay. And okay, so now I have to make sure that this has the same connections, electrical connections, as the previous current supply. So this remains a 4 ohm resistor. And I still have a second electrical connection up to this 3 amp source. Okay. So there's one. And this has some electrical connection. Okay, good. This bottom route still connects back to that 2 ohm resistor that we're interested in. So we have that. And let's see, what else do we have? Oh yeah, we had the 30-volt 3 ohm supply that we changed out. And again, remember, it still has the same electrical connection. We haven't touched the 6 ohm circuit, so we'll leave that there, that 6 ohm resistor. And what we have changed is right here. I'll go ahead and draw it like this just to make it more apparent. Okay. We have 10 amp supply and our 3 ohm resistor. There we go. Now, I'm sorry, I know that took a little bit to draw out. More often as we move further, maybe I'll probably just cut scene and then have the new one drawn in. But it's good to practice redrawing them because you might inadvertently change some electrical connection and didn't mean to. Okay, so be careful about that. In fact, I see right now I could probably change this upper part, this upper right-hand part, and this bottom, or excuse me, upper left-hand part. So those 2 pieces I could probably do. Well, looking at the upper left-hand part, we see that there's another source transformation that can be performed. Okay. I think what I would like to do is change that upper left-hand part into a potential supply. Then once I have it in a potential supply, I can combine the left side of this circuit into a single supply. Okay. So let's go ahead and do that. We have a 3 amp and 4 ohm supply and resistor. Sorry, that's not a 9, this is a 4. And we're going to change that. So what does this end up becoming? It is a 12-volt supply in series with your 4 ohm resistor. Okay. Good. And now notice that we're slicing off essentially this whole left side of the circuit. So I can redraw that. We can draw that as, well, keeping the bottom left-hand side the same for a moment. This is a 4 ohm resistor. This is an 8-volt supply, so I'll leave those two untouched. Now we notice that we have that junction right here, where I've taken the 4 ohm 30 amp parallel circuits and I turned it into a 4 volt or 4 omega and a 12 volt supply. There's 12 volts. Now I need to make sure that that electrical connection stays the same, so I have to connect at this node. So there's where I connect. This side still runs back to that 2 ohm resistor. And I'm going to go ahead and redraw this upper right-hand portion. And I will draw it in a slightly more suggestive manner. We have our 6 ohm. We have our 3 ohm. And we have our 10 amp supply. And I'm just redrawing it to highlight the fact that up here in this upper right-hand corner, we have resistors in parallel with a current supply. Well, now you notice, if we take a look at where we were originally, you have basically these 2 current supplies right here, and it's unclear, they're not strictly in series, but it's unclear as they are drawn how we could combine them. Especially because there's some junction, there's some node right here that siphons some of the current down that line. Okay. So it's unclear how we might be able to combine those. But after some source transformations, we have now decreased, if you will, the number of essential nodes in our model. What this means is that the result of that is now we have a couple of potential supplies that are in series, namely the 8 volt and the 12 volt. And that we know how to deal with very easily. We can add those together. Okay. And in fact, what I'll do is in this upper right-hand corner, we'll make that into a potential supply as well. And so then we can add all 3 of these supplies together. So before we do that, we have our 3 ohm resistor and our 6 ohm resistor. We need to find the equivalent resistance. So 1/3 plus 1/6 and -1. Well, let's see. Okay. Sorry, this one I always like to think of a clock, right? 20/60ths and 10/60ths gives me 30/60ths, or 1/2. So this whole rigmarole is going to be equal to 1/2. And of course, 1/2 to the -1. So at the end of the day, we get 2 ohms. I'm going to go ahead and redraw this on the next page just so that we have a reference figure. And I'll go ahead and combine that left-hand side of the circuit. Okay, we're almost in the home stretch. We have another source transformation to perform. So now we have the 10 amps and the 2 ohm resistor. So what does that give us? That gives us 20 volts in series with a 2 ohm resistor. I don't know what I'm doing there. So we have 20 volts in series with a 2 ohm resistor. And again, I'm just taking care of that upper part. And notice the direction of the high and low. And just emphasize, since the current supply is causing current to go from right to left, that means that the high side of my battery or my potential source is on the left-hand side. Well, now you probably see the interesting piece. I have my 8 ohm resistor. We'll draw this in. I have my 20 volt supply, which is directly connected to a 20 volt supply and a 2 ohm resistor. And keep in mind that 2 ohm resistor is different than the one that we're actually trying to analyze as the load. Right, that one's here in the lower right-hand corner. And last but not least, right? So what's the current flowing through this? 0. Right? The potential drop, if you will, across our load resistor is 0, and therefore the current through my load resistor is going to be 0. So at the end of the day, we did that whole rigmarole, and we found out there is no current flowing through our load. Pretty cool. Okay, so let's try one more for kicks. Here we go. Example problem. Okay, so here's another example problem for us. Yeah, let's go ahead. We want to find the current flowing through the 1.5 ohm resistor. Go. You got it? Yeah, good. Okay, so as we go through, I see that there's 3 places where it seems that naturally I can combine the circuit. So I've got this left-hand piece, which I will highlight rather than circling because highlighting is a lot cleaner in post-process. So I've got this leftmost piece. Okay. I've got this top piece. And then I've got this branch in the middle here with the potential supply. So let's go ahead and convert those to 3. This left-hand piece, I can convert that into a 12 volt supply in series with that 6 ohm amp. So that's the left-hand side. This top piece right here, I can convert that into, I'll put a plus and a minus, a 5 volt supply in series with my 5 volt amp, or my 5 ohm amp. So that's what I'll do for that one. And does that, let's see. Yeah, this last one, I can convert it into a 2 amp supply in parallel with a 17 ohm resistor. And we'll put that like that. So this one's a little easier to identify what I can change out really quickly. So let's go ahead and redraw the circuit with those changes in mind. So I have now 6 ohm minus plus and our 12 ohm resistor, 12 volt supply. Then we have our 6 ohm resistor. That hasn't changed. That goes in series with our 5 ohm resistor and a 5-volt supply. Okay. And then we have a branch with a 2 amp. Excuse me. Look at this. Right here. That's the wrong direction. Should be down. There we go. That's an ugly down. Should be down. Down. And we have a 17 ohm resistor. And then we have finally our 1.5. And I'll leave that open right there just to remind us that that's where our connection's supposed to be. This comes down. Okay. Well, now we're in a position, we see that we have a couple of potential supplies that we can combine. We have a couple of potential supplies that we can combine, right? This 12 and the 5, and the resistors as well. So let's go ahead and do that combination. And I'll go ahead and use this white space up here. Right? So no extra fancy stuff needed. We have a 17 ohm resistor. And we have a 17 volt supply. Then, what else do we have? We have a 2 amp supply. And we have a 17 ohm resistor. And then we have our 1.5 ohm resistor. Sorry, I'm running out of space there. Well, now I've got to figure out how to exchange the 17 volt supply, or combine the 17 volt supply with the 2 amp supply. Now you might be tempted, you might say, hey, why did I have to do this exchange in the first place, this current supply? Okay. Keep in mind that we would have had 2 different voltage supplies in parallel had I not done that switch. So we are going to need to exchange this guy, this left-hand side. We're going to have to turn that into a current supply. Then we can finally combine our current supplies in parallel, and then we can convert back if we need to. Actually, we won't. Okay. So this last source transformation is this left-hand side. And that's because, conveniently enough, 17 and 17. That gives us a 1 amp supply going up in parallel with a 17 ohm resistor, in parallel with a 2 amp supply. So this is 2 amps going down. A second 17 ohm resistor. It's almost like somebody actually thought out the numbers. And then our 1.5 ohm resistor, our load. But now we're in a situation where we can combine these suckers, right? We can combine the 1 amp supply and the 2 amp supply. Namely, that is a 1 amp supply going down. We can combine our 2 resistors, which are in parallel. And since they're the same value, this would just be 17 over 2 ohms. And then last but not least, we have our 3 over 2 ohms. Huh? Hey, we have a current divider again. And so the current flowing through our 1.5 ohm resistor is the value of the other resistor, so that's 17 halves, divided by the sum of the two resistors, well, that's 10, times the total current, which is just 1. So we get something that says 17 over 20. Let's see, 17 over 20. Okay, so it's 100 minus 15. Okay, so we get 0.85 amps. Now that's the value, the magnitude. Bear in mind, I naught was specified to be running clockwise from top to bottom through that 1.5 ohm resistor. We find that instead, the current will be running from bottom to top. So technically we should put a negative sign in because it's in the opposite direction of what the specified direction was. So I'll say that I, in the 1.5 ohm resistor, the final answer I'll have as 85A. The negative sign coming into play because it's actually from bottom to top, not top to bottom. Okay. Cool. So hopefully you see the utility of the source transformation in particular circumstances. Again, I can't tell you exactly, but sometimes you can look at a circuit and do a bunch of source transformations to arrive at the answer without too much fussy Kirchhoff's laws, subbing and solving, matrix multiplication. It gives you sometimes a more elegant way of working through a circuit without having to do a lot of extra calculations. Okay. Cool. Well, I think that's plenty of example problems for you for right now. But the next step, the next thing that we'll cover is Thevenin and Norton equivalent circuits. Okay? And again, it feels a little bit like these source transformations to a degree. And yeah, good times. Hey, thanks for your attention. I'll see you next time.